Well, thank you everyone for bringing me here. I've had a great time. It's been very, very interesting. Just as a reference to yesterday's talk, our Australian system is going through a fairly dramatic restructure of education system at the moment, and one of the sort of indications of that is my faculty has just been restructured, and I've been lucky enough to find myself in the new, not even a school anymore. We're not quite sure what these things are, but it's the something or other of information sciences. So we've developed all these quite new sort of approaches to university education and research, and it'll be interesting to see how that comes out. But I'm quite happy to be in information sciences. I thought IT was not really a place for me to belong, but information sciences is great. So let's see how this works. Okay, so what I'm going to be talking about is, I figure it's a system science conference. So I'm going to actually try and consider my work over the last, I guess, 10 years as a system and try and work out what I've been doing, because it seemed like a good opportunity. And given that I haven't been around for very long, it seemed like a good idea to to talk about things that I aim to do in the future, or things that I'm currently doing, because, you know, I haven't actually done that much yet. It's all hopefully in the future. So what I'm going to start off with is a bit of a motivational thing, and then we're going to get into quantum light models, and hopefully that'll justify the work that I'm currently performing, but I'll move through this quickly. So firstly, we'll just start off with high-end complexity and what on earth it is I'm talking about when I talk about high-end complexity. So when I finished my PhD thesis, I was young and naive, and I thought it was reasonable to actually take a look at complex systems, and a reasonably critical look at complex systems, because one of the problems I sort of see, at least in Australia, in terms of what we're doing with complexity or with system science, is we're looking at simple complexity a lot. So there's a lot of work that's going on in fields like network theory or agent-based modelling or information theory, or there's a lot of people working on systems at the reasonably complicated, slightly complex kind of area of work. And really, the reason why a lot of people went into complex systems theory is because they were interested in very complex systems. So, you know, I'd like to know about language, or I'd like to know about the mind and how does cognition work, and biological systems. They're fascinating, absolutely fascinating systems. So the stuff that I'm very interested in is this area down here. And what you find when you are very interested in that area is there's very little work being done in the actual generalised modelling of these systems. And a lot of that is because it's just very, very hard. So there's not a lot of formal theories that can deal with these things. And part of the problem to me with that is fundamentally to do with the contextual dependence of these systems. So the meaning of a word depends on the other words around that word. You can't just identify meaning without reference to the context of a word, or the fitness of a creature, the fitness of an animal has to be defined in the broader context of the system that creature is found in. So there's attempts to sort of get at that, but I you know, a couple of years ago was feeling a little bit grumpy, so wrote a paper where I was trying to sort of encourage people to work more at the high end of this scale, so this concept of high-end complexity. Now, interestingly enough, I find myself now not too sure about this, so it was a first attempt, and I find myself a little bit worried about it. So, for example, the idea of a system being complex is always going to be relative to the person doing the looking, the observer. And this is, I think, what George was getting at with his concept of an experimental frame or an experimental thing. So if I want to analyse projectile motion in a very complex way, I can put a lot of different variables in. I can think about, you know, I can get a very complicated analysis built up. But generally, it's never going to be something that I can think about as, it's never going to be as complex as, say, biological development. So just as a proof of concept, the systems that I'm going to talk about today all fall here. So just as we can develop theories at this end of the scale, and this is what I'm pretty much spending my life trying to do at the moment, and hopefully I'll get somewhere, but I'll have to wait until the end of my life for the next systems science sort of retrospectives conference where I can tell you whether or not I've actually done it. So just as I guess a rehashing of that, at least in Australia, the system science movement, or complex system science, is pretty much what it's called now. In Australia, there's not much work on system science per se. People are doing lots of network theory and lots of agent-based modelling, things like that. So they're looking at, say, Bayesian statistics, or they're looking at sort of statistical mechanical models of complexity of many body systems. And they're coming up with great models. They're very useful models. They work very well. But I would like to actually sort of posit for you that all of these models assume fundamentally that the systems that they are modelling, so all of these theoretical approaches, take separability as a starting point. They assume that the systems they're modelling are separable. So our best models of complexity are assuming the very thing that we as system scientists set out to actually try and get past. We as system scientists were assuming that our systems were holistic and you had to analyse them together. They all take non-contextuality as their starting point. So they assume that the system is in some way defined relative to a context, and that context doesn't change in an important way. And the thing is, most of the systems that we're currently interested in don't behave like that. So in terms of complex systems, I wrote that, and then I went looking around in my study for some examples, and these were the ones that I just came across quickly in the space of half an hour. So for example, we've got Eberhard, Mary Jane Eberhard wrote a book on developmental plasticity and evolution, which is talking about how one genotypes of the same organism, if put into a different context, a different environmental context, can develop a completely different phenotype to the extent that you'd actually identify the thing as a completely different species of animal. Or we have Alvanoa over there, who's talking about action and perception, and how if you actually want to understand how we perceive objects, you need to understand how we act, and how we act in the action of perception. So that's a phenomenological approach. We've got over here a book that's a collection of works looking at schizophrenia and how different countries will actually yield different sort of diagnosis of schizophrenia and different eventual outcomes of schizophrenia in terms of the treatment of the patients. And the different people in this book are relating that to the culture that you find this diagnosis or treatment occurring in. We've got someone up here in Nature writing an article about the need for economics to come up with a more scientific approach, and talking about the Black-Scholes equation, and so how that actually generated, in a sense, the stock market crash in the 80s. So essentially the model that you used to describe the system led to a fundamental change in the dynamics of the system itself. You can't assume that your models are separate from the thing that you're describing. Oh, I can't even work out what that one was now. So, this was about immunology. This one over here is about decision theory. We've got a different Ellis over here talking about the need for causality, a more Aristotelian kind of approach to causality, and the need to actually consider things like final cause, or why did people build a house, or why these concepts are necessary if we're going to understand humans and human decision making, human approaches to systems. So I mean these were just a fairly random. Oh, we've got Robert Rose in here talking about the need for different models of complex systems. So you actually can't model the same one system using one model, a very complex system anyway. So these are just books that I thought of looking around in my library, or articles I'd been reading that week. So I mean, what we find is across all fields of science, there's a need to incorporate context. And we're failing, we're fundamentally failing. So this is, how are we going to start succeeding? And we need more models. That's my sort of claim, especially at that high end of the complex systems scale. So the rest of this talk is going to be devoted to my attempt at developing more models, and I'm by no means claiming this is the only way to model these systems. I don't think it is. It's the only one that I came up with, so it's the one I'm working on at the moment. So that work in the first part of this talk was essentially where I was coming at the end of my PhD. So I wrote this paper sort of while I was looking for a job. And then I got this job at QUT, which was looking at applying quantum theory to the modelling of semantic structure. So we're attempting to model meaning. And the reason I'm working in an IT department or information sciences department now is we're attempting to do this in order to, make better models of, better search engines. So we're trying to come up with better ways of actually finding information in the web. So I'm sort of the tame physicist that helps all these IT people. So, words and meaning. Let's start, that's interesting. Let's start with an experiment because it's the end of the day. Boxer. If I say boxer, what are you all thinking of? Anyone thinking of anything? Are you thinking of someone that punches people? Okay, so how many people want to stick their hand up and say, yes, I'm thinking of someone that punches people? Okay, so that's a fair whack of people. Is anyone thinking anything else when I say boxer? A dog, okay, so there are two meanings to boxer, okay? There's actually far more than two meanings. But boxer is, it's an ambiguous word, and those two meanings are completely different. So you have a type of dog, or you have a person that punches people. You also have someone who puts things in boxes, maybe. So you could come up with almost, an infinite number of things that this term means. But the dominant meaning that you find is a boxer is someone that punches people. Interestingly enough, different countries, and here's another contextual effect, you'll have different dominant meanings. So if I say boxer in Australia, I tend to find that dominantly people think of a dog because boxing's not a very big sport in Australia, so it's not very common that people would think of that. So let's go a little bit further. If I say I petted the boxer and he licked my hand, the people who had originally been thinking boxer was someone that punches people might start now feeling a little bit confused and decide that, oh, actually I was talking about something else. I guess the boxer could be licking your hand, but anyway. So the point is that the word boxer in a different company, in a different set of words, will have a very different meaning. So, Firth coined this term that's quite widely quoted of "we shall know a word by the company it keeps." And it's a very nice principle. We know our words from the company they're in. And what you find is humans are exceptionally good at extracting that meaning. I mean, we're very, very good at forming a hypothesis, thinking, oh, we're talking about, a dog, but then changing the hypothesis on the fly as more data becomes available. And in fact, there's a form of sentence called a garden path sentence, which is a bit of a curiosity, where you can actually confuse people very, 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 well, a lot, by leading them up the garden path. You essentially force people to think of a sentence as having one set of meanings, and then midway change the sentence into the other set of meanings for these words. And you find people kind of go, but after maybe 5 seconds, they actually work out what it was you meant. So humans are exceptionally good at doing this. Whereas if you look at information science technology, or you look at search engines, or you type something into Google, it can't deal with this, okay? Our technology just doesn't deal with this sort of on-the-fly abductive reasoning. We just don't do it. Well, it doesn't do it, but humans do. So, more interesting things. Some meanings are more dominant, so we've already seen that with our experiment. So, for example, a few more sentences. The bat flew across the room. Are we thinking of, well, what kind of a bat are we thinking of? So there's actually two meanings, again, here that we could talk about. We could talk about a bat in a cave flying across the room, which would probably be the dominant meaning and the most likely meaning that people would, come up with. Or we could talk about a baseball bat, for example, or a cricket bat flying across the room. Now, both of them make sense, and you could actually settle upon both of them. But generally, people will settle upon a bat in a cave. The boxer drooled on my hand. Again, the dominant meaning is the dog. And what we're seeing is all of this stuff depends on a lot of factors, so contextual factors. So it depends on social, historical, cultural things. And what we're doing at the moment, we're investigating some of these effects in terms of the combination of two words, so concept combination, because this is a very interesting thing in IT at the moment. So looking at trying to model words not as just bags of words, but actually looking at the semantic relationships between these words. But the stuff that I've been doing in terms of the quantum modelling stems from the work of some experimental psychologists, Doug Nelson and Kathy McEvoy in Florida, University of South Florida. And they've spent 30 years, and the more I work with psychologists or biologists, the more astounding it is. Like, physics really does nothing in comparison to, psychology is astounding. I would never have the patience to be a psychologist, but my respect for them is growing by leaps and bounds every time I sort of have an email correspondence with these people. So they've spent 30 years collecting free association data, looking at how people associate words. So if I say bat, what does someone give me back? And they've turned this into these very, very large word association networks or data, modelling the way in which modelling the associations you can form between these different word sets. So for example, up here on the left we've got the word planet, and we've got planet's associative structure. So we've got the list of all the words you can get to from planet, and then they've modelled the associative structure between those words. So at the moment, because we're only looking at the words you can get to from planet, we haven't got, for example, eternity appearing on this association network, because people don't tend to associate planet directly with eternity in this case. So they've spent 30 years collecting these very, very detailed maps by torturing all of their first-year psychology students. I guess they hand out leaflets and make them fill them out. And then they've taken this stuff to a higher level by generating extra list queuing data. So an extra list queuing experiment is an experiment you run by giving people a set of target words and making them sort of memorise these words, and then giving them, during the experiment, exposing them to a queue and asking them to recall a word from that list of target words. So for example, you might give them a list of bat, ball, glove as their sort of target training list, and then give them the word cricket as a cue, and you'd see which word those people come back with out of that target list. And it's called extra list because the cue was not in the list of words that you trained these people with. And so they've generated this massive amount of data. And what they find from these experiments, what they find is that the standard models of how humans associate this data don't quite work. So the standard model of people's word associations is generally called spreading activation. That's the very well accepted model. And what it sort of says is if you give someone a cue, you would imagine the activation of a person's semantic network just gradually spreading through the network. So if I gave someone the test cue universe, essentially the activity would spread throughout their mental lexicon, activating all these different words, and eventually they might settle on the target planet, okay? But the standard, this spreading activation model essentially says that activation can only spread in the forward direction, so it can only follow the arrows. And what that means is that, for example, while you could imagine the spreading activation as spreading through space up to planet, so that's a viable pathway, and people could associate those words and recall target that way, you won't see people, according to this model, sort of activating a planet by thinking universe star planet, because they had to go backwards against the arrow halfway through. And what Nelson and McEvoy have found is that that's not true. Actually, there's an effect that star path is actually possible, and it is actually it's a verifiable sort of effect that you can actually find and statistically analyse and find is significant. So they came up with a model of this based on quantum theory and called it spooky activation at a distance, which was a very ad hoc model and not very nice, but it was a good start. And so we started working with them, and what we're doing is coming up with a model that's a more formalised model based on a quantum-like approach. And this work has just been published this year in the journal Mathematical Psychology. But I'm just going to talk about the basic idea here. I'm not going to talk about the actual. So the basic idea is we represent the target word to be recalled as a vector in just a standard space, a standard vector space. And what we imagine is it's a qubit, so it's actually a quantum space at this point. And what we say is that when a person is presented with a Q, they might either recall the word or they might not recall the word. But, you know, one or two of those results are going to eventuate. And what you'll find, what we're representing, the recall as sort of a 1 in this space and the not recall as a 0, so just your standard not or yes kind of response. And what we find is we can link that to the probability of recall in terms of how far along that basis the thing projects. So when you collapse it down, you're going to have a certain probability of recall based upon how far you are along that axis. Now, this becomes interesting in a quantum-like approach because, and this is where context becomes important, we could just as easily choose a different basis. So up here, we might be talking about the chances of me recalling bat in the context of the Q ball. Okay, so I've got a certain probability of me recalling bat when given the Q ball, and it's B1 squared because we're sort of taking a quantum approach. But I could just as easily choose a different basis where I'm talking about my probability of recalling bat in the context of the Q word cave, say. So essentially what we do is we talk about these two different basis states, and we can represent our probability of recall using one or those two basis states depending on the context. Now this is a very simple model, and it's you know, much more developed, and there's a lot more detail in the article. So rather than boring the people who don't know anything about quantum theory, I'm going to keep moving on. But this is the basic fundamental idea. So we can represent context using these two different basis states. Okay, so another way in which quantum theory is being used at the moment, and this is work that's being done by Jerry Bussmeyer, Ricardo Franco, Didier Sornet is doing it as well at the moment, quantum decision theory. So we're going to quickly talk about how irrational human beings are. And this is quite a problem. Humans are irrational. So what you find is that humans violate a whole heap of laws that are fundamental to standard probability calculus. So there's a thing called the sure thing principle, which would say, well, if I prefer something in the context A, and I prefer it in a different context B, then it's a sure thing that I'm always going to like it. So for example, if I like Indian food in Australia, and I like Indian food in India, then it's a sure thing that I like Indian food in Australia or India, isn't it? It's you know, it's an obvious thing. But what you find is humans consistently violate this. Not in all cases, obviously, because I do like Indian food in Australia or in India. But you can find throughout the literature, and Shafir and Tversky, who again I'm developing very large respect for, have found they did a lot of work on this in the 50s and 60s, I think it was. And so they found things like this. So this is a classic example of it. Essentially, Alice is concerned about sort of, you know, the US presidential election, and what you find is always share prices drop after the US presidential election. I didn't know this until this happened, but so it's a very silly thing to hold on to your shares before a US presidential election because the price of those shares is going to drop. But what you find is that humans always wait until after the election to go and sell their shares, and we know that because the share prices only drop after the election. So the logical thing for us to do would be to sell our shares before the election, but we never do, okay? And in fact, this effect happened after the second Bush election. There was a quite pronounced drop in the share price. So this is a classic example. There's a whole heap of other ones, like students taking vacations and lots of stuff. We've got another one, and this is called the Linda problem. And let's just go through the example. So Linda, okay, but don't read the answer. Okay, so Linda is, 31 years old, single, outspoken, very bright. She majored in philosophy. Now, as a student, she was deeply concerned with issues of discrimination and social justice, blah, 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 blah. Now, I want you all to be honest here and hold up your hands. Which is more probable? Linda is a bank teller? Who thinks that? Linda is a bank teller and active in the feminist movement. Who thinks that's more probable? Now, the second one's more probable? Okay, be honest. How many people are holding their hands up? Come on, all of you. Okay, and this is a standard effect, okay? 85% of people surveyed choose that. Now, this is a very, very standard violation of a very basic fundamental tenet of probability theory. So essentially you have all just violated standard probability theory. And what you find is the only people who, the people who tend to fall in this 15% of actually getting the right answer and agreeing with standard probability theory, they tend to be the people who've done statistics or, you know, understand probability theory. So what you find is, because essentially this is a combination of two statements. So this is Linda as a bank teller and active in the feminist movement. That's actually a far more specialised statement. And it is actually it's just as likely, it's actually less likely than this one because it's more restrictive. So you'd be far more sensible to just go, well, she's probably a bank teller. It's more probable. But humans don't do that. Okay, humans almost never do that. It's incredible, okay? You can actually find experts in fields making statements like that, okay? Now, this is not necessarily concerning, but it is concerning when we're thinking about current drives, you know, in the world. So, you know, if we think about people trying to sort of form integrated assessments of our effect on the globe, so carbon, sort of global warming, essentially urban forecasting and urban planning, if you think about global agreements and negotiation processes, all of these things are going to depend on us having advanced, sophisticated models of how humans make decisions. And most of our decision theory models are based on essentially standard probability calculus. So at this point I get concerned and I'd like to come up with better models. And so there's a fairly standard sort of approach that a lot of people are taking. So Busmai just got a paper into Proceedings Royal Society of London on this, and Yukolov's Sornet. This is a very nice paper, but it's currently under review, so it's not available. And what they do is they essentially make use of your standard probability calculus, but add to the probability an interference term that is based upon a quantum sort of modelling. And what you find is that this interference term represents the way in which these different worlds can compete with each other and actually affect each other. So what you start talking about is the way in which humans, when they're faced with uncertainty, have a tendency to shy away from decisions. And you represent that using this uncertainty factor, which is essentially a cosine, which is sort of talking about the way in which the worlds interfere with each other. And what you find is that in certain situations, you can actually match the behaviour of humans far more closely. So the details are all in the papers, but just as a sort of a standard example of how these things could interfere, let's say someone was deciding to marry. So, you know, should I choose person A or should I choose person B? You know, who should I marry? But let's say they all were also at the same time trying to decide what they were going to be in their future life. So, you know, I want to be rich maybe. So should I become rich by being a gangster or should I become rich by working hard? Now, what you'll find is these two decisions, these two different sets of decisions, they might actually interact with each other. So for example, if you're trying to get rich by becoming a gangster and the person A who you want to marry doesn't believe in gangsters or, you know, thinks that that's a terrible way to become rich, then you probably shouldn't marry person A. So these sets of decisions, they interfere quite profoundly. And what you'll find is you can model that using a quantum approach very nicely. It's a very elegant model. So that's another one. So final thing, this returns to the work that I was sort of doing in my PhD. So a bit of history, this has all been talked about before. We were playing with my PhD with a pregeometric model, and what you do is you sort of set up a big matrix and evolve it, and you find that the matrix has a tendency to make structures that have a certain form. So they tend to form tree-like structures, which are sort of nicely embeddable in a spherical structure, and you can sort of argue that they have something like three-dimensional sort of behaviour. But there's sort of these extra bits that we were kind of arguing as knots or tangles and things. And essentially these defects you could think of as sort of like a matter term and da-da-da-da. And what you find is this equation is nonlinear, and it's very open because it's got a noise term. So you could sort of argue that that's contextual kind of relationships. It's also highly non-local because of this nonlinear term. So every element in the matrix depends on every other element from iteration to iteration. And what we had was this equation came from QCD. And what we'd done is we'd stripped away a lot of the sort of space-time and charge-specific information and sort of just played with the structure of the equation. And we found that it generated some very interesting behaviour. And so this is what led to my interest in systems theory, because I found that it's a very hard equation to analyse. So these matrices are very, very large, and it's very, very hard to extract any kind of information from it at all. Like, most of the analysis goes to trying to understand what it is you've generated. And so I went looking in hierarchy theory and artificial life and lots of different places for ways to actually analyse the behaviour of the system, which is where we came back to sort of the first part of this talk. And what I came back to is quantum theory seems to be doing something here that's important. So quantum theory, the structure of the equation as inherited from quantum field theory, seemed to be the thing that was useful. And I don't know how much time I have to do here. So what we kind of come to in terms of a theory of what quantum theory is doing is quantum theory has 4 minutes, you said. Let's get this. We'll go straight through to this. Okay, so we'll come straight to the major hypotheses of my work. And this is sort of the grand program that I'm working on at the moment. So the theory is, well, the hypothesis is, quantum theory is a theory of contextually dependent complexity. And there's a lot of different parts of quantum theory that can be used in different ways to describe this. So, for example, it describes the manner in which the systems that we're interested in can depend on other factors. So that's other contexts. And those contexts could be within the system itself, and you can do that via entanglement, but I didn't go into those details. You can do that, you can talk about the context of the system and our ways of looking at it. So you can talk about the measurement of the system via the measurement theories in quantum theory. And you can look at essentially the system and the environment, so contextual dependence that way, and that's open quantum systems. And the other sort of hypothesis is that quantum field theory, the important thing about quantum field theory is it's actually got a essentially infinite number of ground states that stems from the fact that you're dealing with a unitarily inequivalent set of theories. So you actually come up with a far richer set of theories when you go to a full quantum field theory. And that enables you to talk about ontological emergence. So you can actually talk about the true generation of novelty. And that's something that I was doing in my thesis and I've been doing later. At the moment, I'm trying to come up with a quantum field theory of words, so of semantic meaning, but it's very difficult. So this is the grand sort of agenda of my work that I've been working on. And I guess I would need another 50 years before I can tell you if it's actually been successful or not. But it's showing some promising results so far, so we're going somewhere with it. So just in summary, contextually dependent systems, they're everywhere, okay? They're absolutely everywhere. But we have very, very few formalisms dealing with them. And the very nice thing is that quantum theory does appear to actually provide us with some very good theoretical tools that we can use in modelling this. There's a lot of very big challenges in this, so most of the people doing this are really just looking at measurement theories, so they're playing in Heisenberg representations and things like that. Time evolution is very problematic for a sort of a non-quantum approach. So if you're dealing with quantum theory of language, for example, you don't have the space-time symmetries that people use to construct time evolution of a quantum system. So essentially the way in which you come up with your evolution equations has to change, or you have to come up with a different set of symmetries that you can use to do this. We need rigorous definitions of contextual and non-separable sort of systems, and that's something that I'm working on at the moment. We need generalised quantum field theories, and there's, you know, one big question is, well, this would actually really imply a different interpretation, a new interpretation of quantum theory. So there's a whole set of philosophical issues to be dealt with there. And so, you know, just as a plug, I've got a new grant working on this, and most of this is for a fellowship for me, but I need PhD students. So all of your bright young, however many of them, there were millions of them, I was very impressed. If you don't have a place for them over here, then you're welcome to send them over to me, because I'm looking for PhD students at the moment. So just as a conclusion, thank you very much. These are some of my collaborators and some of my students, and thanks for everyone for bringing me here. So thank you.